The purpose of this lecture is to discuss the response of second-order systems in time and to try and extract core characteristics of these systems. Having already covered the case of critically damped systems whose transfer function looked like 1 over s plus alpha squared, we'll now look at the case where we encounter other cases. So for that purpose, let me repeat our study. It is the time response of second order transfer functions. So we are now interested, we have covered this case, 1 over s plus alpha squared. Okay. And now what I would like to cover are cases where h of s is equal to 1 over s squared plus 2 zeta omega 0 s plus omega 0 squared. If you remember, just like here, we will put a scaling factor so that the step response of the system always converges towards 1. The equivalent here would be to use alpha squared on the numerator. So interested in this, we now are interested in covering the case when this denominator has 2 real distinct roots. Under these conditions, we can write that equivalently zeta squared omega 0 squared minus omega 0 squared, which is the reduced discriminant, is strictly greater than 0, or in other terms, zeta squared is strictly greater than 1, or zeta is strictly greater than 1. Under these conditions, we have 2 roots. One of them will be S1 is equal to minus zeta omega 0 minus square root of delta, and the other S2 will be minus zeta omega 0 plus square root of delta. These 2 roots must be less than 0, otherwise we will have an unstable system, and we assume we have a stable system. This is automatically ensured when zeta is positive. We can rewrite these roots as S1, 2 is equal to minus zeta omega 0 minus or plus times square root of omega 0 squared times zeta squared minus 1, or this is equal to omega 0 times minus zeta minus or plus, depending on whether it's the first or the second root, times square root of zeta squared minus 1. So the way to further our work is now to reduce this transfer function using partial fraction decomposition, like we have done earlier. For that purpose, I will erase this area of the drawing area, and I will say that h of s is equal to a over s minus s1 plus b over s minus s2. Now I can reduce this to the same denominator, and I obtain this must be equal to a s minus s2 plus b s minus s1 divided by s minus s1 times s minus s2. The bottom we know is equal to this, and therefore we obtain that this must be equal to s times a plus b plus minus a s2 minus b s1 divided by s squared plus 2 zeta omega 0 s plus omega 0 squared. And this is because the product of this is just a factorization of these guys. From this, we know that there is no s term, therefore a plus b must be equal to 0, or b is equal to minus a, and we obtain that a times s1 minus s2 must be equal to omega 0 squared, since this is what that says. So we know that s1 minus s2. So let's see. We can skip all this. And continue our calculations. So we have that s1 minus s2 will be equal to minus 2 square root of omega 0 squared zeta squared and minus 1. Or in other terms, this is equal to minus 2 omega 0 times square root of zeta squared minus 1, which yields a is equal to minus omega 0 divided by 2 square root of zeta squared minus 1, and b is equal to omega 0 divided by 2 square root of zeta squared minus 1. We replace a and b by their value in the transfer function. And we say that so we replace this by minus omega 0 divided by 2 square root of zeta squared minus 1. Okay. Let me rewrite this. This is not very nice. Let me put a and b back, because obviously I don't have the room to do that. So what area can I clear? I will clear this area here. And I will say that the transfer function h of s will be equal to, let me factorize out 1 over 2 zeta squared minus 1, and we take the square root of it, times we're going to factorize also omega 0, and we're going to say it's going to be minus one over s minus s1 plus 1 over s minus s2. This should do the trick. Okay? Now, we can analyze these two things and see what happens with them. For example, we are possibly interested in the impulse response of H. We know that the impulse response of H will look like something like this. Okay, let me erase these guys. Okay, now I have A and B. We can erase these guys. Let me redo that. There's been a mistake. Let me do that again. I really want to erase this area. So, if we want to look at the impulse response, we can look at the impulse response of first minus 1 divided by S minus S1. The impulse response of minus 1 over S minus S1 is the inverse Laplace transform of this fellow. Now, this will be minus e to the minus S1 t. Now, S1, so I can write it as explicitly as minus e to the minus zeta omega 0 times square root of, oops, my mistake, times let me erase the zeta as well. Minus e to the minus omega 0 times zeta plus square root of zeta squared minus 1. Now, the inverse Laplace transform of my 1 over S minus S2 will be equal to e to the minus omega 0. My mistake here, e to the minus omega 0 times zeta minus square root of zeta squared minus 1 times t. So both of them look like decaying exponentials. This one starts at minus 1 and grows up. Okay? So what it does is something along these lines. And that one does the same thing, but starting from 1. And it decays. Now, because this number, which is positive, is smaller than that number, we know that this exponential here decays slower than this one, such that, since this one starts at minus 1 and that one starts at 1, this quantity is always positive. And the sum of the two exponentials will be something that starts at 0 and then we'll move on to do something like this. And it will die off pretty quickly as far as this effect is concerned, and it will espouse the top exponential. Let us look at this from a more computational standpoint. So we will pick an example where zeta is greater than 1. So we'll say something along the lines of zeta is equal to 2. We pick omega naught is equal to 10. We set the variable s as our running variable, and we define the transfer function as we said omega naught squared divided by s squared plus 2 times zeta times omega naught times s plus omega naught squared up. This is our transfer function. Okay. Now we can ask for the roots of the transfer function. Okay, denominator. We say that a will be equal to minus omega naught, minus omega naught, yes, times zeta plus square root of zeta squared minus 1. With a is equal to minus 37, blah, blah, blah. Now we write b is equal to minus, we're going to say minus omega naught times zeta minus square root of zeta squared minus 1. And you see that it is still a negative number, but a much simpler one. If I define fun1 or tfun1, transfer function 1, is equal to 1 divided by s minus a, and tfun2 is equal to, hold on a second, yes, so minus 1 divided by, so tfun1 must be its opposite, okay? Why? Because it is associated with the inverse Laplace transform of the most negative of the two roots. So we say tfun1 is equal to minus tfun1, and we write tfun2 is equal to 1 divided by s minus b. We'll take care of scalar quantities, the factors, later. If I write, if I do the simulation of these two guys, okay, and what we will do is we will if I choose t is equal to 0.0510, and I want to plot the system. Okay, so I say tfun1. I should obtain something. And that something is a fast decaying exponential. In fact, it is not even very pleasant, the way that it does not decay. That may come from my lack of resolution. Sometimes you can get an inappropriate result by simulating a transfer function over too small a time step. This is typically the case here. So what we're going to do is we're going to change the resolution here and go from 0.05 to 0.005. We will also restrict our simulation to something shorter. If I want to have my response again, oh, this is because I'm computing a step. My bad. Okay. So what I wanted was the impulse. And now I get what I want, which is a fast-growing exponential, which decays quickly to 0. Now, if I take the second one, oh, and by the way, that fast-growing exponential starts indeed at -1, although it's hard to see. Now what we're going to do is do the same for tfun2. The net result will be a much slower decaying exponential, and such that the sum of the two will be something as follows, which is that the system starts at -1, sorry, it starts at 0, it goes up very quickly and then dies off like the second exponential, because the first one is dead. tfun1 is dead very quickly, and so it espouses tfun2. We can hopefully zoom in. Let's see what happens. Something is not clear. Okay, forget about zooming in. Okay, now, is this the real transfer function? No. Because we then need to multiply it by ω0 divided by 2 zeta squared minus 1. Okay? So we're going to say that the impulse response scales up to this. Now, let's talk about step response for a change. So for that, I will erase all this, keep my system, and say that the impulse response of that system will be in the Laplace domain omega 0 divided by 2 zeta squared minus 1 times the inverse Laplace transform of one over S minus S2 times 1 over S. Okay, again, we're talking about the step response. Minus the inverse Laplace transform of 1 over S minus S1 times 1 over S. The best way to understand this is to do a partial fraction decomposition. I know that you would much rather look at a table, but I believe that there is some good into being able to recompute these quantities online. And we will say that 1 over S minus S2 times 1 over S, we will write as C over S minus S2 plus D over S. And we quickly find that this is CS plus ds minus S2 divided by S minus S2 times S, and therefore C plus D is equal to 0, and minus ds2 is equal to 1. We get therefore that C, we can write D is equal to minus C, and D is equal to 1 minus 1 over S2. Therefore, writing that erasing these calculations here, something went wrong. Okay? We're gonna write that 1 over S minus S2 times 1 over S must be equal to 1 over S2 times S minus S2 minus 1 over S2 times S. Now, when the impulse response of this, or the inverse Laplace transform of this is fairly easy to see. It is made of asymptotically of that step. Okay, so let me use another color. Okay. Now, time t is equal to 0, these two things are equal. Therefore, the system starts at 0. And you see this term is a growing but stable exponential of this kind. Now, we have the same for s minus s1, except there's a minus 1 sign in front of it. Okay? So, if I were to look at s minus s1, okay, I would need to take a negative axis for the system and then say that this guy would actually go down to, whereas this one is 1 over s2, that one would be going to minus 1 over s1, and it would be a other exponential which now would go towards minus 1 over s1. Eventually, the sum of the two must go towards 1. We're going to put it here. Okay? And this is the scaling factor for it. Now notice that s minus s1 converges to 0 much faster than 1 over s minus s2, the inverse Laplace transform of that. So that the net sum of these two exponential will be an exponential which would go this way, okay, once it's weighted that way. And these two competing exponential will actually go up, not down. Now let's look at this for a second by seeing how it works in MATLAB. We have tfun1 and tfun2, and we're going to do tfun1 first. Okay? Instead of computing the impulse, we will compute the step. Let me erase the picture so that we don't mix everything together. When we look at the step response for tfun1, which corresponds to the fastest eigenvalue, it goes down to a certain value. And that certain value is about minus 0.27. We could always say that so it's 1 over s, 1 over a, okay? And we indeed have that 1 over a is minus 0.026, okay? Which is exactly where this guy tends to station, okay? It's 6, 7, okay? So it's about here. Now, let's do the same thing, but for tfun2, okay? So we do the step, and we obtain that the response for tfun2 grows much higher, okay, and reaches some steady state value. it is easy to see that T fun 1 plus T fun 2 will do a little bit of what we've talked about before. Okay? That is, it will grow to some value, and then will always be positive because these two exponential compete, but this one cannot beat that one. And indeed, if we try and zoom in the best we can see the detail of the start, which is that the function starts with a slope equal to 0 and then climbs up here. Now, it doesn't quite reach, so that's the sum of the two, okay? A positive term plus a negative term gives a term in between. Now, of course, in order to get the true step response, we need to scale it by what we said was omega 0 divided by 2 squared zeta squared minus 1. Okay? So we're going to say that we're going to weight the two transfer function. So this will become omega naught squared divided by square root of zeta squared minus 1, and then we multiply this by T fun 2 plus T fun 1. We look at the resulting picture, and indeed, oops, that's incorrect. This is because I need not plot omega 0 squared. It's my mistake, it's omega 0. Wrong picture. So we get it to converge to 2. What was my mistake? Oh, I forgot to divide by 2. Okay, so first we'll erase this picture, and second we will divide it by 2 everything, and this time we get what we want, which is a step response which goes to 1, that's the role of the factor omega 0, and which is always positive. Okay, so it's almost like, but not quite like, a true exponential. Okay, so move my mouse. Oh yeah. Okay, because if you go here and you look at the details of what happens at the start, we have a slope which is equal to 0 at the start. Now, in this particular thing, we have the notion of rise time. So the rise time is the time at which the system goes up to 0.9. And in this case, the rise time would be about 1.3 seconds. This is very important. The notion of rise time is a notion of responsiveness of the system. The second notion that we see is the settling time, which is how much time it takes to go from 0 to a certain percentage of the final value, say 0.99. We could argue that the settling time here is about 2.5. Okay? So we have two interesting quantities here that we can talk about. Erasing everything, which is in the step response of a system. I draw the two axes here, time, and then 1 over s, h of s, the inverse Laplace transform of that. Okay, we have a system that does this, and the rise time is to start about, this is 1, so you start at 10% here, you end up at 90% here, you compute the time at which it was 10%, in this case about 0, the time at which it reaches 90%, and the time it takes to go from 10% to 90% is called the rise time. Then, as the system settles, then there is a point at which you are always within a band of about 1%. You can choose other percentages. Your computations will be slightly different, but the goal remains the same. And then the time it takes for the system to settle within 1% of its asymptotic value is the settling time, Ts. So that's rise time, and that is settling time. We will talk about how to compute them later. Let's see. In this particular case that we have covered, if we go back to our function, you can see that much of the growing exponential is dominated by the inverse Laplace transform of 1 over s minus s2, because s2 is less than 0, but it is much bigger than s1. Okay, this one on the order of minus 2 blah, and this is one on the order of minus 37 blah. In that particular case, we can compute the two answers. Okay, so we said A, B is equal to minus S2, A is equal to minus 37. We are good. In this particular case, as I said, because S2 is so much bigger than S1, we can compute and say that the settling time and the rise times are about those of the inverse Laplace transform of 1 over s times 1 over s minus s2. Okay? Up to a scaling factor. We know that this Laplace transform is really about starting at 0 and ending up at there. We can take this, and what will we obtain? So I'm going to erase this. Oh, wait a minute. I'm going to move this. I'm going to erase that. To make room for my derivations. So we know that my transfer function and my response is going to be 1 over S2 times 1 minus e to the minus S2 times t. When is this equal to 10% of its initial value or its final value? So the final value will be 1 over S2. Okay? So when is it that 1 over S2 times 1 minus e to the minus S2 t is equal to 0.1 over S2? Okay, so we're looking for t, that t where things are, where the rising exponential is about 10%. I can erase this, I can erase that, and obtain that e to the minus S2t must be equal to 0.9. Of course, we can compute, therefore, that t must be equal to minus natural log of 0.9 divided by S2. Okay, so that's for this point. Now for this point, it will correspond to the computation of e to the minus S2t is equal to 0.1. And so if we call t1 this time here, at which we reach 10%, and t2, the time at which it reaches 0.9 times its final value, then we're going to get t2 is equal to minus natural log of 0.1 divided by S2 again. And the rise time will be t2 minus t1. Will be minus log of, and we can, by the way, say 0.1 divided by 0.9 using the multiply additivity of logs times one over S2. Okay, and this is not 0.2, my mistake, this is 0.9. You could say that this is approximately minus log of 0.11 times 1 over S2. Okay? Now for the rise time, so that's the rise time. For the settling time, we just keep saying e to the minus ts S2 must now be equal to, we said within 1%, so it is equivalent to saying that this is equal to 0.01. And likewise, we get Ts is equal to 1 over S2 minus 1 over S2 times natural log of 0.01. And we see that this is about, this is much slower than that. This guy is longer than this guy. Okay? So this is the end for today. The next lecture will be devoted to the analysis of oscillatory systems in time. That is the case when zeta is between 0 and 1. This is by far one of the more interesting cases, and we never have zeta is equal to 0, but this is by far one of the most interesting cases. Thank you.